So now we have our second speaker for today, Professor Huang. Professor Huang received his PhD degree in electrical engineering from National Central University. And before coming to Tsinghua as a professor, he worked with MediaTek for 3 years, where he involved in chipset design and optical storage products. And since 2002, he has been with our WE department, where he is a full professor now. Professor Huang's research interest is in circuit design for communication, biomedical, and power management applications. And today he's going to share with us again about baseball, but from the aspect of acoustic sensor, I believe. Okay, let's welcome Professor Huang for his talk.
Okay, thank you everyone. Good morning. So I'm Prof. Huang from the Department of Electrical Engineering, National Tsinghua University. Actually, this is my first time to present this topic because I think this is our first start to work on this field, especially on the signal processing, led by Professor Ma. So I think that before that, I will thank my students that work very hard just from the crash to work on this field. The topic I will talk about today is about the baseball ball bat impact position estimation by acoustic. Due to the limited time we have, so I will not go very detailed about the technical issue. Instead, I will tell you about the application of this kind of techniques. Okay, so as the title, we want to understand the ball bat impact position. Actually, this kind of factor will not be reported at the state of like a system like the Statecast in MLB or something like in every kind of baseball broadcasting system. However, I think that to understand the impact position can help especially on the training. For the player, they can understand how far their hit away from we call that the sweet spot. Therefore, they can improve their hitting performance. For the coach, I think that because that's to understand actually that with eye, if you want to know the impact position, I think that is very difficult. So with this kind of tool, the coach can analyze the players' techniques and give them some suggestion to improve. And the other issue is from the manufacturers. For the bat manufacturer, because that's the invasive techniques, I think that they can do some invasive tests. They can understand the quality and the uniformity of their equipment. Okay, before we start our techniques, I think that we have to understand today that's available tool that to maybe just has a potential for understand the hitting position estimation. The first one you will think about the video. Okay, I think that today that is a very popular popular approach to understand every detail of your game. This is a poster-oriented structure, and most important, that is non-invasive. That's good, but there is a very, from the cost point of view, that's a very costly. Because they have to, we at least need a 2 or even more high-speed camera to capture every detail from the different angle to construct the 3D image. So they need, besides of equipment cost, they need a very precise setup and they need a lot of calibration to make sure that the mismatch between each camera can be calibrated. And for extracted information, because that is a high-speed camera, there's a huge data set, so the computation complexity will be very high. Even though that the time and the signal resolution, due to the sign of the angle, there's some limitation. So actually, that's from the cost of view, I think that's the main limitation. But even though you will see that statecast, because there's I think that is there's a lot of market, you will see that they can achieve a very high resolution, and you can see that very details for your base, especially for the baseball. Another approach, there's some, as the Professor Ma said, that they try to use inertial sensing or some pressure sensors to test the movement-oriented action. Okay, there are advantage. That is environment insensitive, but instead they are invasive. That means that that is Garmin's product. They say that is impact. They need to attach a set, a small set at the bottom of the bat. Okay, to understand the swing phase of the base of the baseball. Okay, so they need a extra attach. Of course, for the official game, that may not be allowed, and there's due to the sampling rate limitations, so that's the resolution limit. And I think that at current state, although they always show, they also show the heating procedure. At this moment, they cannot provide the heating precision. Instead, they just give a trajectories of the swing. Okay. Let's go on the next page. So before our detail, I will try to let you listen three sound. Okay. Okay. Let's go on the second one. And the third one. Okay, let's go on the next page. Actually, that's three clips that's from the last year. The player is Otana. Okay, the first one is actually is a home run. Let's see the detail. Okay. Okay, you will see that the sound is like this, and the second one is actually that's the pop-up, and the third one. Okay, actually the ground. We try to use acoustic information to apply them for the baseball. This is the basic experience. When there is no TV broadcasting service, okay, when I was a child, we can only just wake up at midnight and to listen to the radio. Okay, so you may think how old I am. Okay, so that give us a hint. Could we just give, instead of a video or sensing, could we just use acoustic as valuable information to extract something that from the, especially for the heating process. Okay, let's go on. Okay, let's go on the video. Before we start our analysis, I think that we have understand the physics of the ball bat collection. Actually, this is a very high-speed camera. Okay, I download from the YouTube because actually that I cannot get such a high performance videos in my group. So that's the camera can achieve around the 10 kilo frame per second. Okay, so you will see that. Let's go on the next one. Okay, why do we need acoustic as information? Because I think that is physical-oriented performance. Different impact position will lead different physical interaction between the ball and the pad. From the experience, you will also see that for the good hitting, they will give a very clear sound, a very nice sound. We say that Japanese say that's a hito. Okay, if not, you will see that they will give other kind of sound. But I don't think that is not so easy to use the mathematical equation or physical equation to describe the such a complicated interaction between the ball and the bat. Okay. And I think that may be a good tool. The acoustic may be a good tool because they can intrinsically achieve a very high timing and signal resolution. For example, that for your cellular phone, if you open the recording, you will see that at not a hi-fi quality, just a CD audio, you can get a sampling rate that is 44 kilohertz and 60-bit that's with 96 dB dynamic range. I think that's much better than the existing either video or sensor that can give us. Okay, the third one. Okay, compare with the other approach, you will see that's easy to set up. Okay, if you want to record the sound, actually that you don't have a very complicated, dedicated setup. And this is non-invasive, and you can just use your cell phone. That will be a low-cost solution. Okay. Why the ball and the bat collection that will make sound? Because they will make a vibration. We say that's come from the vibration for ball and the bat. We say that's vibroacoustic. I think that is quite a classical knowledge or field. Okay, that is we just use the ball as an example. We say that's mode 0, 1, 2, 3, 4, 5. Okay, when you hit the ball, they will reform the ball, and when they be squeezed and relax, they will make a vibration. That's for ball. And for the bat, they will also have a bending. Okay, that's also have the first mode, second mode, and the third mode. Okay, we can just raise our curiosity about if this will make noise, make sound for us to record. So we can do some preliminary test. Okay, let's go on the next one. Okay, this one, that we use the toss method to test, real test the bat and the ball when we hit the ball and record his result. Before that, we will see that the time is very short. Okay, because that's maybe just within a millisecond range. Okay, and we don't know this kind of we don't know that what we record is what part is from the ball and what part from the bat. So we also do the following test. The next one. Okay, this is we just use a solid hammer that to hit the ball. You will get this result. From this result, you will see that there's most in the high frequency. Okay, Instead, if we just use the same hammer that's to the back, you will see the curve like the green one. You will see that there will be some deterministic swing, and that's located at a lower frequency. If you try to put these two in together, you may think that okay, you can get the one that's the curve as a blue. We try to depart this waveform with three parts. The first part is that the ball that's approaching to the bat. They will first go for the screen phase. Also, you will see that is there includes some big sound and the high frequency part. Okay, when they squeeze to the limit, you will see that almost the high frequency part is eliminated. So there's only a small part, the low frequency part is caused by a major come from the bat. Then third part, the ball that will leaving, just snap back away from the bat. And you will see that the high frequency part will again appear. Okay, so you will see that this is the time variance system. During the difference phase, you will get a difference response either for the power, the amplitude, or the frequency. Okay. Because that is not a mathematical problem, so we need real data. So we just asked some expert that's to help us to do some real data collection. Of course, we just want to test the heating, okay. But we also need ground truth to understand what is the exact position when this heat happen. So we use the carbon paper. They just stick around the bat, and we by understand the mask of the ball, we can understand at least the distance from the top. Okay, and the player that we first select the 7 first tier. Actually, that will be a profession. Most will be the professional player when they graduate from the university. And the 3-1 that is not to the top, but there's also a class 1 university player. And we select 8 with the right hand and the 2 with the left hand. And for the test, to guarantee the quality, so we not use the real high speed throw. We just use a toss method. The method will like this. That is the short range with light throw to control that most of the heating will cover the range we are interested. But we also use 3 types, that's the ash, yellow burst, and the maple bat for our test to understand if the output performance will greatly influenced by the different kind of different material of the bat. Okay, for the data. Okay, finally we just collect the a little less than the 400 for label data. Okay, we just delete some outlier. We just get the result that between the 10 to 90 centimeter. For the bat, we estimate that the sweet spot may around the 15 centimeter from the top for each bat. So when the data set is ready, we build up our machine learning. Actually, because we try to at the start we try to build up some physical equation to try to solve or at least give you some direction. But I think that as you see that the waveform is very non-uniform, so I think that it's not easy to have an equation to know every detail, every parameter. So we just think about use the machine learning to do that. Okay, so like actually there's nothing very new because we just use existing machine learning algorithm. We just use two in parallel part for the feature extraction. The first is 2D, that is time frequency analysis. So that as the time goes by, we will analyze the frequency component distribution and put them into the convolutional neural network. Besides this kind of analysis, we also apply the concept that the attention-based structure, that we add some time domain features, some frequency domain features that's based on the expert experience, and put them into the fully connect neural network. And at the output, we try to combine this information to predict the position. Okay, and because due to the limited sample we have, we cannot build a very complicated machine. So at this moment, under this condition, we can achieve almost a real-time response. Okay, and this demo can be. Yeah. Okay. Sorry. Actually, okay. You will see that's the toast method, and this is the demos and be placed in the one sports festival, and you will see that the impact position can be reported almost a real time within second range, and because our data set is between the 10 to 19 centimeter. If the error tolerance within plus and minus 2 centimeters, that's about half of the ball. Okay, that's the accuracy. It's about 82%. For the higher tolerance is allowed, maybe just a little smaller than the ball. Okay, accuracy can be higher than the 90%. Okay. Okay, this is not the conclusion. We just write some discussion. This is our first step to understand the ball bat impact point estimation. Our result just demonstrates that this may be a feasible approach to understand the information, the performance just within a very short period of time. Okay, as you see that we just collect the data under the limited range. So if we want to make this system practical, we need more data to cover all the possible variation. Maybe the variation will be covered the ball speed, spin, or the wind, or whatever, and the possible variation that for a different player and the different position that's outside the range we have. And moreover, if we need to know if the ball will be a pop-up or the grounded, we need more information, just the position instead of distance. We also need the top or the bottom of the bat. Okay, this is a lot of work. Okay, but if we have for our next step, we hope to extend the data set, and at the same time with deep learning techniques. can be applied. We hope that not only for the accuracy, but we hope that will cover all the possibility to make it real. Okay, of course, this is just one possible techniques because we just listen the sound. Okay, but besides the heating behavior, if they do not make sound, okay, we can get any information from these techniques. So I think that if we talk it for the holistic system, data fusion, okay, that's mixed with video to understand the posture, understand the ball philosophy, the angle, the trajectory, and some sensor to understand the swing phase details. That's all needed. If we can integrate all the data, I think that we can achieve a more holistic system for report more details about the baseball sports. Okay, thank you.
Thank you, Professor Huang, for your talk. Any question from the audience? I have one very quick question. So you mentioned that there are many factors that will affect the sound when the bat hits the ball, right? So which factor do you think that will affect the accuracy of your solution the most?
Okay, I think that is a quite good question. Actually, that in our application, actually, that what we care is about the position, or we say that's long distance from the top of the bat. Okay. However, if you want to know the flight's trajectory, not only on the position, there's more on the top or the bottom during the hit phase. Okay, but the difficulty is that we put 1 centimeter as a report solution, but for the top and bottom, I think that's maybe just 1 order smaller than this one. That means that they may make a different sound, but the resolution will be very limited. Okay, so that means that we need a more even for get the ground truth. I think that's the more difficult because you will see that the precision will be very small, but the sound may be, or the performance maybe has a large difference. Okay, this is our next step. And I think that's another issue we are now dealing with is about the noise. Because in our test, that is a relatively quiet bullpen. But for the real case, I believe that there's a lot of players that's working together. I think that because we hear the sound, that the noise will be a critical issue that we have to deal with. Yeah.
Right. Thank you. Any other questions from the audience? So if not, let's thank Professor Huang again for his excellent talk, and this will conclude our today's seminar. Thank you, everyone.